Hey guys, for chapter 1.5, we're going to continue doing the logarithms. So what we're going to do is understand how to read the logarithms such as ones that are on a graph. So right over here, we have two definitions, actually three definitions. So we know that a limit is something that when it gets to a certain number, then it's going to equal something to the range of it. So the definition for this one is we write the limit where if the function of x approaches c from the left. If we can make values y equal f of x arbitrary close to your L, by taking x to be significantly close to the c, where your number is x less than c until it's left. So the left is going to talk about, you see that negative sign right in front of right behind the c, the x approaches the c negative? That means in this photo right here, we're going to focus on the left. So if this is the x and the arrow is pointing this way, what are the dots going up to the letter x or the letter A? What are the dots that are going to go to the letter A? And that is going to be part 1 of it. Part 2 is the complete opposite. So if the limit of the function of x is equal to L, where the x approaches c from the right by taking x to be sufficiently close to c, where x has to be greater than c, that is going to talk about this example right here. So if A is your c, then you have to count the dots and see where the trend is from the right side, so that A is going to be on the left. So x has to be greater than c. On the last part, otherwise the limit does not exist, or D and E, if you were to put it in its actual homework assignment answer form. So let's try out a problem. So here are a few problems that we're going to take a look at. The goal of this calculus idea is we're going to try to show you the final answer, and we're going to try and backtrack to basically how did we get there. So first things first, let's talk about these three things right there. So the limit of the function of x, where x reaches the positive 3, where it's on the right, how does it equal 2? This is actually supposed to be negative 3. So negative 3, how is it going to equal 2? So here's negative 3, and that tiny hole is going to be 2. So from the right side, we count the many points, and eventually it gets to 2. So that is how we got 2 right there. How about the limit of the function of x, where x goes to negative 3, but we add? What about that part? The limit of the function of x, where x is going to reach negative 3 with a negative, is going to be 2. But how do we get there? Well, since it's going to be a negative, we're going to put that negative 3 right there, and we're going to start here. So on the left side, as it goes up, it reaches the number 2 on the y-axis. So that is how we got 2 as the answer. The same kind of logic goes with the second one right here, where if it's the limit is going to be 2, that when the x reaches negative 3 from the positive side on the right, when it goes down, it still goes to the number 2 on the y. But when it goes to the limit of the function of x, it's going to be 2 either way, because if this reaches 2, if this reaches 2, and that reaches 2, logically we can safely say that the limit of negative 3 in general is going to be 2. But what about happens if we have the function of negative 3? the function of negative 3 is not going to be anything. The function of negative 3 is going to be something. It's going to be 1 because we have this tiny filled in bubble dot, which means that something counts there. It's the 1. So that is going to be part 1 of understanding how to solve these by reading a graph. But wait, how did this problem get undefined? Well, if we have the function of 2 right here, the function of 2, nothing's really listed, and that unbubbled dot does not count. So since there's nothing defined, it's undefined. The limits do not care about the functions. So even if something's not really a function continuously, or if it doesn't really work out, limits have a separate form of logic where there still can be limits if the function doesn't really exist. Let's try and look at another kind of scenario that we're going to take a look at. So we're going to try and solve the first 6 problems right here. So this is going to be the graph that we are given. As the x approaches negative 5, and you have a negative sign, we start right here. And as it goes up to that negative 5, that is going to be 3. So that is how we got a 3 right there. But if we have x, and we have negative 5 as the limit, but then we start going down, if we start here, and then we go up to here, that makes no sense, because that is going to be equal to 1. But that also doesn't make sense how if this is 3 and that is 1, then the third one is not going to work and it doesn't exist because 1 cannot equal to 3. So the third one, it does not exist. The one previously, the one shown right here, it does work because this equals 2 and that equals 2. Since we have 2 and 2, logically the third one should be defined. So going back to here, since 1 and 3 are undefined or doesn't exist, it cannot work. Now we can take a look at, whoa, how do we get these infinities here? Let's take a look at negative 3. So negative 3 is going to be right here. This is negative 3. So as the x approaches the negative 3 to the negative on the left, it goes down to negative infinity. Since that you start at negative 3 right here again, and then it approaches from the right, it's still negative infinity. And since negative infinity equals negative infinity, then logically the third one is going to count as negative infinity. Just like how it logically was the same for this one, where we have 2, 2, and 2. So, what happens next? There's one more thing that we should take a look at. And yeah, it's chaotic. It's the function of sine 1 divided by x. So in trigonometry, you probably should know about the sine of 1 divided by x. But there is only one condition. Yes, the x cannot be 0, because if you put 0 as a divisor, it becomes undefined. So logically, we can say that if you start here, it makes a normal sine wave. That happens when you have whatever is there greater to be 1. But as you start dividing, like 1 divided by 0.99, or like 1 divided by 0.25, or like 1 divided by 0.000000013, then that's why all these waves are going to get more tightly and tightly compact, and it's going to get a lot crazier and crazier and crazier. And the center right there, if you try so hard to zoom into a graphing calculator, 0 is going to be the hole where it can't be defined, because you can't divide by 0. And this is what really happens. Every time you have a limit where the sine of 1 divided by x, and it goes towards these things, you can't define them, and it does not exist. So yeah, that gets extremely, extremely chaotic. Let's try to actually solve that out. So right here, we have a -5 and -3. And we have those tiny sine waves that are going to go crazy and crazy and crazy. And since we have the limits go to -5, and then the limits go to -3, then it's going to does not exist because n cannot be 0, and that also does not exist either. So yeah, that is how we dig deeper into understanding how to graph and understand the limits. Thank you for watching Black and Purple Math and Ministry. Like and subscribe.